bottom line, we've got 120 volts difference between this recording. Turned it on, I think, but I want to make sure. Okay, it is. The answer is yes. So here's what happens in this schematic. We've got two lights, series or parallel? Parallel, yeah. Yeah, they're connected to the same points electrically, so they're in parallel. So disregard this R1 section for just a moment. If we push PB1 and PB6, PB5, and PB4 are not engaged, then that actually applies a voltage to the coil of the relay, right? R1. Yeah, R1, relay 1.
Yeah.
So we can press PB1, we can press PB2, and we can press PB3, and we can energize the coil of the relay, right?
Correct.
Now let's look at what we're doing with the contacts. Pin 8 is the common pin of the relay on a typical 8 pin. And pin 6 is the other end, the normally open side. Very good, thank you. So what happens is, when we press that button, R1 becomes engaged, closing this contact, providing 120 volts to this light right here. Well, R1 and R3, our pin 1 and pin 3 of R1 are also contacts. This is what we call a double pole relay. And we're providing 120 volts here. So what that does is it keeps this rung, and this is called a rung in ladder logic diagram, it keeps this rung true. So what it does is it latches the 120 volts that we're providing to the coil. So follow that for just a minute. When we press PB1, several things happen. R1, the coil of that relay, and I've got that relay up here. R1 receives voltage across the coil. That closes that normally open contact, right? Well, if you look at this relay we had yesterday, and I'll pass it back around, there's two sets of contacts on here. This is what we call a double pole, I should say, and double throw relay. So I've got a set of contacts over here that when that relay is energized, closes, and I've got another set over here when that relay energizes, that closes. I can hook whatever I want to those. They're mine to use, whatever. So if you look at the front of it that has the writing on it, you'll see a couple of copper contacts, and both of those engage when we apply voltage to the coil. The normally closed go open, the normally open become closed. So as soon as we press a button, we send a voltage to that relay. Once we press that button, 120 volts is provided through the contact that's tied to pin 8 over to pin 6, turning on this light. Now if it weren't for this part, these contacts, as soon as we let go of that button, that light would go off because the coil would be energized and we'd have no voltage. But what we're doing is through pins 1 and 3, just like we have through 8 and 6 to light the bulbs, we're providing a voltage through them that's in parallel with all the switches that keeps that voltage active to that coil. And that's what we call a latch. So what we've done is we press this button. As soon as we press this button, it energized this coil, making those lights come on. Now if we didn't have this in here, as soon as we let go of that button, no more voltage to our relay would shut down, therefore our lights would shut down because the normally open would go back to its normally open state. But what we did was we took the other normally open, as soon as this button is pressed, both of these pass their voltage. This one passes it to the lights, This one passes it in parallel with the switch that we're pressing closed. And by doing that, it keeps voltage going to that relay, and it keeps those lights on for us. And the only way we can turn the light off is by breaking the circuit. So if we press PB6, PB5, or PB4 in that circuit, then that relay shuts down. No applied voltage to the coil. Everything that's normally open returns to the normally open state. The normally closed stuff is no longer normally closed. So, excuse me, I think I said that backwards. I did say that backwards. If it was normally open, it opens up, and if it's normally closed, it goes back to the normally closed state. Yeah, I did say that backwards. So that's how we can latch a relay. And it's kind of nice because the main part about this that's so nice, we have a power interruption. As soon as power comes back on, we don't have to worry about this coming back on to an on state. The only way it can come back to an on state is if we press a button to set it back. So as soon as we lose power, either through Georgia Power shutting down or by breaking this circuit, this thing's going to be shut off. So let's see if I've got the software installed. Hey, hooray! So we were buying a little time by looking at that. Now let's see if it'll actually work. Right. There is a software guide. So let's look at that actual circuit. And let's see if what we saw holds true. Let's do a little better than that. Straighten up. So it's got a very zoomed in screen on the monitor. Not amazing. And maybe it's synchronizing now. And okay, sort of. Not quite. Let's just see what happens. Explore that circuit. We're just going to operate it. We're going to pull a meter out and see if what we said holds true. I guess it has to sync every time it changes the resolution.
So that circuit with the lights in it, those lights could actually be motors or anything that you're controlling, correct?
Right. Yeah, we're just doing a lot. And if you look on this relay, it's a little hard to see. We see pins 5 and 6 are our normally open and normally closed contacts, as are pins 3 and 4. 2 and 7 are our coil, and 1 and 8 are our commons for that relay. So, and actually, I don't know if the reference, yeah, the reference doesn't show that. So anyway, we can see our relay. So let's look at our schematic, and let's see if what we think is happening is happening. I'm going to break out the meter here in a moment. And right now, we know we should read a voltage across PB1, PB2, or PB3 because the lights are not on, right? What should we read across any of those 3 switches?
Say it again?
120. Let's see if that's true. So across my switch.
Can I take this home?
115.
Yeah, it says 115 on this paper.
Well,
I'm
okay.
sorry, man. It looks like fun.
You know, there's technical people and then there's technically technical people. I found the technically technical people in this group. That's good. That's a valid point. Yeah, it is 115 rather than 120. It's one of those things that is hard to get away from how you normally reference AC there. But yeah, in this case, we're reading 115 volts. So what is going to happen, what all is going to happen when I press that, any of those switches?
It's gonna drop to Z.
We'll drop to 0 and
The light will come on.
lights will come on. Let's see
Should.
if that holds true.
Should.
And it does. It's hard to see the difference between the yellow and the white until you get used to looking at it. But there is off, kind of a dull gray. There's on, kind of a whitish yellow. So yeah, sure enough, that voltage changes just as we suspected that it would. Now, what we're saying is happening is as soon as we press one of those buttons, we're engaging the coil of that relay. And if you look over there on your connection wiring diagram, you see what I was talking about. Pins 2 and 7 are the coil. Take a look, you see the little circle that represents the coil going to pins 2 and 7. Pins 1 and 8 are the commons for the contacts. We've got two sets of contacts. One that has pin 1 that feeds the normally open and normally closed 3 and 4, and pin 8 which feeds 5 and 6. So, what do you think right now with the lights off will read across pins 2 and 7?
2 and 7.
2 and 7.
115.
If we read 115 across the coil, what should be happening to our relay?
Should be energized.
Should be energized. Is our relay energized? So, ergo, what do you think would read across our coil? 0. Let's see if it's true. So we're going to the coil side of our relay. And we're reading 0 volts. So what would we have to do to see that coil energized?
Turn it on.
Push the button.
Push the button. Let's see if that holds true.
You gotta transfer the voltage.
All right, so sure enough, 114.8, some mild line losses. We see the indicator that our coil is energized. We see the approximately 115 volts. I did that for y'all. Up there, 114.8. So our coil is energized. Now, we said a couple of things happen. Let's turn it back off. We said that the very first thing, or at least one of the things that happened really simultaneously, pin 8, with it off. Now, remember when we talk about voltages, we can relate to across a set of contacts, or we can relate to a pin reference to ground or neutral. So be careful you understand what I'm asking here. But if I were to read pin 8 voltage relative to ground, what am I going to read there?
Pin 8 relative to ground.
Pin 8 relative to ground. Let's see if it is. So I'm going to put my black lead on the ground.
Should read 115.
Look at your wiring, that schematic diagram on the left. What do you think I'm going to read on pin 8 relative to ground?
Should read 115.
115.
Cause that leg goes straight, comes down to pin 8.
That's right, we've got a direct connection.
Okay, yeah.
Right. What do you think is going to happen as soon as we turn that circuit on to pin 8?
It's going to 0.
And the lights come
Will it go 0, you think?
Still got your direct
Let's see. This is where it gets a little
No,
quirky.
you got it on ground, it should stay at 115.
It's going to stay 115. Again, it's how we relate to, and this is a point I want to make sure we all get in our heads, because our point of reference
Still referencing.
often changes our perspective. Now let's do it the way probably many of you were thinking in your heads. I'm going to turn it off. And I'm going to go between pins 8 and 6 here. Now I'm reading 115 between those two pins. What do you think is going to happen when I press that button?
That should go to 0.
That should go to 0. Again, we're changing our reference point. So here's what's going to happen as soon as we turn it on.
Oh.
Right now, if you follow that, if you look at pin 8, we've got a path back to the line, which is where pin 8 is connected to. We don't have any current flow through our lights because they're not on. So we've got a path back to neutral through our lights. So we've got a difference of potential between those two contacts. And this is why I say this is one of the hardest things to wrap our minds around when we deal is these reference points. And that's one of the reasons why they talk about referencing everything to ground. It makes a little more sense when you do it that way. But yeah, as soon as we press on, what's gonna happen is pin 8's got 120 volts. It's gonna pass it over to pin 6. And as soon as it passes over to pin 6, that's what does the work and cuts on our lights, right?
Okay, yeah.
Yes. And still on odds. Let's see if that happens. So yeah, sure enough, we are now at the same potential rather than the difference of potential. And now, relative to ground, both pin 8 and pin 6 will read 115 volts. But if I turn it off, pin 6 doesn't, but pin 8 does. And the only way I can get pin 6 to be 115 volts relative to ground is to make that normally open contact close. So what we did was we handed off the 114.8 volts that was on pin 8 over to pin 6 and turned on our lights. We're also doing that with the voltage at pin 3. So let's see if it pretty much behaves the same way. We're going to go to pin 3. What should we have relative to ground on pin 3?
Right now, zero.
Zero.
We do. Now we're going to go to pin 1. What should we have?
We should have 115.
We should have 115, and we do. So what's going to happen when we press that on button to pin 3?
It'll go to.
It'll pass that 115 volts that's on pin 1 over to pin 3, and this is what latches our circuit for us. If it weren't for this contact, as soon as we let go of that button, no more lights. Lights out. Oh, I'm sorry. So there we go. God, I'm on video. Lord help me. So yeah, as soon as we press that button, that 115 volts that's sitting on pin 1 goes over to pin 3. And whereas we were having to press a button, any of these 3 buttons before, to make those lights come on and energize that coil, now pin 1 and 3 are bypassing or jumpering those contacts. So that's what's latching this circuit in the on position. Everybody follow that?
Yes.
And again, if we break that circuit, no more lights, because we did 2 things. We removed the voltage from the coil by breaking either PV4, PV5, or PV6, which in turn means we no longer have voltage passing from 1 to 3 or from 8 to 6. So that's how we shut our lights down. So I think we've got a rudimentary understanding of what's happening here.
Now, would pressing PV 2 and 3 do the same thing?
Yeah, let's find out though. They're in parallel, so if I press PV2, we can see the same things happening. Pin 3 suddenly has 115 volts, and pin 6 should also have 115 volts. And yep, it does. I'm gonna cut it off. I'll go back to pin 3. I'll press on, yes. And I'll go to pin 6. I'll press on, and sure enough. So it does repeat itself. And again, just to clarify, we're going to get to a box later on that it makes sense to have all these boxes kind of within a box on a shop floor. This is a training type of environment. Obviously, you wouldn't normally see 2 light bulbs in a box with 3 switches 3 inches from one another. I mean, it just wouldn't make any sense. But if we expand this out in the real world, if these wires were literally 10s and 20s feet long, and we have one maybe at that door, one at this door, and one at that door, we have the ability to cut lights on from different locations and cut lights off. So that would be a direct application. It just wouldn't be within a box per se. So the same thing applies here. So let's ask ourselves some different questions about this circuit while we're here. What are we going to read between line and neutral up here at the terminal block? 115 volts, right?
Yes.
So let's try it. Sure enough, what about between line ground?
Zero.
Zero. Oops. Yep, 0 volts. So we'll stay at line and ground. What can we do, what can happen to this circuit to potentially kill voltage at that terminal block? Lose power to the power box. And that could happen for a couple of ways. We go over here to the breaker panel and shut it off. Sure enough, we lose. George's power could be off.
Low fuse.
Well, not there. The fuse is beyond it.
Okay.
Now we could trip the breaker, and that would do it. We could have a broke wire between wherever our source is to that terminal block. So there's a few things that could happen. All right. What am I going to read if I move my red probe from here to pin 1 of the fuse?
If you move the red probe?
If I move the red, should be 115 volts, right? Yep. What about to the other side of that fuse?
Still the same.
Should still
It's
be
still
good.
the same.
It's still the same unless what?
Fuse.
Right. If we all of a sudden change potential on the other side of that fuse, we've either got to have a connection problem with the fuse block or the fuse is blown. That's the most likely scenario. So yeah, we should have 115 volts there. All right. What about PB1 pin 1? What voltage, and look at your schematic, PB1 pin 1, what should we have on PB1 pin 1? 115 volts, let's see. PB1 pin 2.
Zero.
Again, we're referencing ground. So if I come here, I get 0. So if we had, and this is where I say the reference point is always important. We have 115 volts on this side, and 0 volts on the other side. There's a difference of potential between pins 1 and pin 2, right? So if I brought my meter down here and measure across that, I would measure 115 volts either way. But referencing the ground kind of makes more sense, and this is one of the reasons why this trainer will try to get you to stay referencing ground, and that way you don't get the difference of potentials across terminals that you get as far as readings of voltages. All right. So what do I do to make PB1 pin 2 have 115 volts?
Push the
Push
button.
the button. So that the voltage-
This one here?
Yeah.
What about that one?
Yes.
What about this one?
Yes.
Yep. Any of those three would work. Doesn't matter, because if you look, they're in parallel, they're electrically connected. So as soon as I press any of the PBs, I am now passing a voltage. And when I let go, what is holding that voltage?
The
Cool.
coil, yeah.
What pins of that relay?
Number 3.
1 and 3 are holding that coil energized. Exactly right. All right, let's turn it off. What am I going to read on, let's just pick a random one, PB1 pin 4. Look at your schematic. PB1, excuse me, yeah, PB1 pin 4. 0, let's see. Okay, what will I have to do to read a voltage there?
Turn the circuit on.
Press any on button, right? And what will I have to do to make that voltage go away? Yep.
Turn the breaker on.
Okay. I think we're starting to see. Turn the breaker, yeah, that would do it too. So, this starting to become a little more
Yeah, start.
familiar. All right,
Much better than mine.
let's go out here. And we're just kind of take a tour. We've got sound. That's the headphone in our mic. Wow, that's really good.
Clothes on.
Uh-huh.
Diagnose and prepare This program will enhance your troubleshooting training and help you to develop and maintain essential electrical circuits will help you become a better troubleshooter by teaching you a proven, systematic troubleshooting approach and providing you with hours of hands-on experience with realistic circuit simulations. With dozens of different faults to diagnose and repair, this program will enhance your troubleshooting training and help you to develop and maintain essential troubleshooting skills for solving problems on all kinds of electrical equipment.
And you're gonna have a chance to go through this individually. Alright, so the goal obviously is to teach you multiple things. We're gonna teach you some troubleshooting techniques. We're gonna teach you safety. Again, don't place that old meter on live power, or you'll find out real quick what happens. And it's also gonna teach you, how we should expect to see different voltages at different terminals. And so you're gonna go through step by step. I'm not gonna read everything here, but it's gonna take you through some faults. We're gonna go through them together, and it's gonna systematically help you understand a way to troubleshoot the circuit. So for instance, if we were to go back to our schematic, if one of our bulbs isn't lighting, what can we almost know isn't the problem if the other bulb is functioning? Yeah, if we're providing power through the switches, we can go ahead and eliminate that part of the circuit. That's just some of the things we can start to understand, ways we can narrow the size of our circuit down so that we're not beating our heads on something, on the other end of the circuit that really doesn't apply. So you've got a copy of the circuit diagrams. When y'all actually get troubleshooting, I'll give you the troubleshooting technique one. We're going to learn about accidents. And again, meter use and understanding where to place your hands and parts of your body. And ladies especially, I know men wear some jewelry, but bangle bracelets and rings and everything else and electricity, it doesn't mix well.
I can tell you from experience, gold is a very good conductor. You don't have to touch it to get a jolt from it.
Yep.
Get close and it'll jump.
It'll arc.
Wow.
It'll jump to that gold ring.
And you take these things for granted because you wear them, but we had a wave solder machine at work, and I won't mention the maintenance guy's name, just something he didn't think about, but the guy from the wave solder, and this is molten solder, this is 600 and 700 degree solder. He showed him that you could dip your hand down in there very quickly into that molten solder, and because you have oils in your body, it almost repels for just a second. Now, if you stuck your hand down in there, counted to 10, you'd probably draw back a nub, but if you did this right here, you might feel a little warmth, but you don't get burned. He maintains it was an accident, that he was trying to illustrate that. I think is what happened. He forgot about something. And guess what that did? He stuck that hand out in there, and of course that solder just grabbed a hold of that gold and burnt his finger and how. So things we sometimes take for granted. Jewelry is one of them. Again, we're going to talk about systematics. We're going to understand the circuit. We're going to troubleshoot it. And you guys, I told you 18. There's only 12. 18's in the other cabinet that you'll have. You're going to have some basic faults that you've got to find, and you're going to have some advanced faults that you're going to have to find. Each of you will be graded on those. And this thing does a really good job. I'll show you my grade. Bear in mind, I do all kind of things to show, like the other day when I showed you a zap. So you're going to see all kind of stuff in mine, but I'll show you my history here in a minute. So, but first, you're going to have plenty of time to
Electrical troubleshooting can be hazardous. Every year, electrical work-related accidents cause hundreds of fatalities and thousands of serious injuries. You will develop a safe and responsible approach by learning about the dangers involved with electrical troubleshooting, including the two main safety hazards, shocks and arc flash, as well as the best ways to avoid them.
So obviously when we troubleshoot, one of the nice rules that a lot of people follow is keep one hand behind your back when they're working inside of the cabin. Reason for that is it protects you from having a shot go through your heart. So a lot of TV techs, they used to know, used to hold one hand behind their, stick their thumb in their belt loop, and that kept them from automatically and instinctively reaching in the back of the cabin. There's some pretty nice high voltage transformers inside of TVs called a flyback transformer. If you touch it, you'll fly back real quick. Several thousand volts that will make you wish you had never done. So again, I'm gonna have to give you a chance to read all about shock and protection against shock hazard. You're gonna have a lockout tagout lab either through the training we do in December or one in here or both. Very well, may make you go through the entire thing rather than just understanding. So arc flashes, we saw that video yesterday, something you don't wanna be around, and again, you'll get plenty of training if you're around the equipment that can do the kind of arc flash we saw in the video yesterday. So, again, I'm gonna give you a chance to see some of that, and some different things. Cotton. Talked about rayon. If you get any kind of arc flash like that, rayon material, nylon material melts in your body, cotton does not. So I'm a firm believer in cotton when you're dealing with that kind of stuff. In fact, if you work for Georgia Power, it'll be cotton from head to toe. That's one of their requirements. Georgia Power is very particular about their safety program. In fact, a guy I know who worked from the nuclear program, and he said that you get one warning even as much as holding a handrail going down the stairs. And after that, if you don't hold the handrail second time you get down the stairs, you no longer work for Georgia Power. So they're very adamant about it. So, again, it's gonna take you through some of the specifics. You guys will have a chance to see those firsthand. So let's see if this goes through it or if we're just gonna read it. Yeah, I'm probably gonna let you. So let's go ahead and let's go through the using the meter section. It doesn't hurt to review this. So obviously there's hazards associated. Electrical energy contained in many circuits can be enough to cause injury or death. And I'll make sure you follow your company's policy in that regard. You've got both a schematic and a wiring diagram. And the reason you want both is we see these connections between these different parts of the circuits here, but a wiring diagram actually shows the physical wiring that's going on in there. So when you get to try to tracing something, this wiring diagram can be your friend after you troubleshoot it using this schematic diagram. All right, so let's look at these diagrams. From the above schematic diagram, you might think terminal PB1 and 2 is directly connected to, so PB1 pin 2 is directly connected to PB6 pin 4. So again, in our schematics, it looks like these two are there. However, when you look at the circuit that is actually connected, you see PB1 pin 2 is connected to PB2 2. PB1 2 is connected to PB2 2. That is connected to PB6 4. So we have to follow it all the way to here. So there's a daisy chain of wiring that takes place between those connections. So that's why you need both. This is your friend when you're troubleshooting. This is your friend when you start trying to potentially home out wires or do different things. General meter rules, always check the meter before it's used troubleshooting for a voltmeter test, the meter on a known voltage. This is very important. Meters can go bad. One of the things that we teach in electronics, and we haven't really said it in here, but we haven't got on our trainer back there that we are going to eventually put you on one by one. The best way to make sure your meter is good is go to a known voltage. If you're fixing to measure AC, go over there to a socket. When you measure 115, 120 volts on that socket, you know your meter's functioning. But God forbid you go over to a 480 circuit with a bad meter lead, you read 0 volts and go, it's okay, no power here. And you start turning the screws on that thing. So you first want to make sure that you've got a meter that is functioning, and then go measure and make sure you've got a dead circuit. And with an old meter, that's easy. Touch the leads together. But just because it reads ohms, doesn't mean it's gonna read volts. You gotta check each segment of the meter. Be familiar with it, you know, sure, it's safe to use. I've seen meters with cracked casings. I wouldn't recommend that because those components inside the meter are getting exposed to the voltage. So if you're holding a meter with a cracked case, it's just as good as you might be holding on to the lead. Make sure your lead's in the correct sockets. That is an easy gotcha. Last thing you're measuring was current. You're fixing to go measure voltage. And you don't think about the fact that you have to move your leads back. You know, you're on the job, you're in a hurry, you're trying to get done, you just measure the current, had to move your lead to do that. And then you go measure voltage and you're measuring 0 volts because you're in the current section. And you forgot to move your leads back.
There goes your meter.
So always be sure, never measure resistance in a circuit without the circuit locked out and verified dead. Otherwise, you're gonna be buying a new meter. Keep your fingers behind the finger guards on the test probes. If you notice on a test probe, there's a wide part of the test probe. That's a barrier for your hands. That's as close as you should be doing when you're measuring voltage with this thing. Never apply more than rated voltage when the input jacking around. And to avoid false readings, replace the battery. A dead battery, a lot of meters will function with the battery indicator on. They'll give you some wonky outputs when they'll do that. Not all will, it also depends on the state of that battery, but you'll start getting some flaky outputs. So I think you already know how to use a voltmeter, how to read, and here we're gonna see what they recommend.
The circuit used in this demonstration consists of 2 switches and a light bulb. With both switches closed, the light bulb is energized, causing it to light up. A multimeter is available by clicking the meter button. To measure the voltage across the light bulb, select the voltage scale and then drag the meter probes to each side of the light. Note that the meter reads the full supply voltage. If one switch is open, the light bulb is no longer energized and the voltmeter now reads 0 volts. Now, let's move one meter probe to the neutral terminal and, with the other probe, measure the voltage at each terminal. Notice the difference in voltage across the open switch. Using a voltmeter in this way allows you to measure the difference in voltage between any 2 terminals in a circuit.
Good advice. Measuring voltage across the light bulb. What do you think, without even breaking down a meter, what do you think we're gonna read across the light bulb? I didn't fully read. Close S1, see? What happened? Close S1 and S2. Now, measure the voltage across 115. Let's break out the meter. Measure the voltage across the light bulb. So it's actually saying between the terminals of the bulb. Now we can answer. Measure the voltage across S1. What are we going to read across S1?
Should be 0.
Should be 0. Should be no difference of potential there. All right, now, but if we go back and reference neutral or ground, go to neutral. What are we gonna read on the other side of this one?
0. No, you're gonna get about 10.
So we get it all the way down to the load, right?
Yeah.
That's when it stops.
But here, we're at the same position. All right, so very good. And using an ohm meter, we should shut off, lock out, and make sure we're dead before we start talking around the ohm meter. And that just keeps us from being harmed by what can happen when the meter receives that voltage in the ohm setting, if we don't, and harming our ohm meter. It's also important to take resistance readings. There are no parallel paths which give you inaccurate readings. To prevent parallel paths, disconnect the wire from the location you're testing. And so, when testing different locations, you have to remove a wire to get an accurate reading. So if we're reading across contacts, across different places, we take it out one side of the circuit, we can safely measure from that. So it allows us to measure resistance. The following screen is gonna show us how to do that. Alright, let's see what it says.
Before taking readings with an ohm meter, you must always de-energize and lock out the circuit, and then verify it is dead. Now, using the screwdriver, let's disconnect one wire from the light bulb. On the multimeter, select the resistance scale and connect the probes to either side of the light bulb. Note that the meter reads 26 ohms. Remove the meter leads and reconnect the wire. Measuring the resistance of the light bulb, the meter now reads 13 ohms.
Wow,
Cause you got another bulb
Yeah,
there.
very good. Y'all brought it back to DC. I'm proud of you. Yeah, if we measure across a single bulb, just connected to 26 ohms, then we returned it and we measured across it again, we suddenly go from reading 26 ohms, which is just the resistance of a single bulb, to the parallel resistance of this other bulb. And if we have 26 ohms and 26 ohms in parallel, remember it's, if they're both the equal value, we can divide it exactly in half, or we could do product over sum. We could do 26 times 26 over 26 plus 26, and we would arrive at 13 either way.
This lower resistance is due to the parallel path through the second light bulb. This demonstration shows that you need to isolate the component before testing to avoid misleading resistance readings.
All right, let's read the fire instructions. First is, use elevator in terms of, make sure to lock out the circuit and verify it's dead. We'll go to the break panel, turn it off, lock it out, we're gonna verify it's dead. Those are the steps. All right. What is this? Measure the resistance of one light bulb. So what do we have to do?
We have to do one of these disconnect.
We gotta break out our screwdriver. We'll do the bottom one since I did the top like that. Break out the meter. What do we need to set it to?
Can we lock it out, take it out? then?
Lock it up.
We did.
Okay.
Measure it here. Measure it here. 26 ohms. So that's what we measure. All right. And notice it said the cold resistance. Remember I told you when you measure a light bulb, you can't do Ohm's law and arrive at wattage because the cold resistance of that filament differs from the hot resistance as that thing heats up. And that's why light bulbs, if you were to slow them down, they don't just go boom, they kind of go and turn them off and on. They slowly brighten and they slowly dim. You see that a lot of time on brake lights. And I remember the first time I started seeing LED brake lights, you quickly notice, you don't really think your mind notices these things, but you quickly notice, hey, that light didn't kind of fade, it just went on and off. I mean, it's just either there or it ain't. And that's the difference between an LED and a incandescent bulb.
It showed it in that power boards that you showed us the other day,
Yeah.
they get the light bulb.
Yeah.
See that?
Yep, see it slow drink up. All right, so what is the resistance of both light bulbs? What have I got to do?
We have to reconnect that wire.
And I moved my meter lead, so it's far enough to know I can't keep doing that. 13 ohms, 26 ohms, 26 ohms in parallel.
Are you sure?
Just the wrong button.
I clicked the wrong one, didn't I?
Yes.
Okay. All right. Just before we leave, we'll do a practice exercise, and we'll finish this one. Even if we go past 11 o'clock, sorry, Nancy, for people, but we're gonna go home after we do this practice. All right. So, let's see. Let's just see what happens. Let's look at a schematic. So are these lights parallel or series?
Parallel.
They're really isolated with one another. whether that's kind of a trick question. Is there anything in parallel? If I turn on all the switches, it would be in parallel. But I can actually operate one independent of the other, right?
Okay,
Yeah, so that's the difference. That's a trick question. I just wanted to throw it out there. So if I want to turn on this first light, what do I have to do?
You have to close S2 and 2 and 3.
And see, we could have probably followed that by going, okay, I got a fuse, it goes from S1 to S2 to S3, this bulb goes up here, this one's coming back. We probably could have figured that out, but look how quickly we figured it out using that schematic. Let's try it. That seems to be working. But something else you gotta think about, I had to turn all three of them on to get it to come on, right? Could one of these switches be shorted on, say the middle one, and it would still look like this thing's operating correctly? Well, that's one way I could test for a shorted switch.
Turn them off one at a
Turn
time.
one
Turn them off one time. Goes off, comes back on. Goes off, comes back on. Goes off, comes back on. So each switch independently seems to be doing its job. So the aim in 4, 5, and 6. See, if 5 was shorted, we wouldn't know it at this point because changing seeing the changing state wouldn't necessarily do anything. Now I don't have a bulb on here. So we gotta do some troubleshooting. I'll leave our schematic here. So, kinda getting back to some of the things we did, let's hear some suggestions. Where do I need to start?
Ground on
Ground on the,
supply.
supply, okay.
And then close.
Check the close.
Start at
Check
12.
your switch,
The
first switch.
fuse has gotta be good for the other one.
Yeah.
There you go, that's a good term. Fuse.
Yes, that's what,
How can I cut this circuit in half almost instantaneously?
Cut this one off.
So I'm talking about as far as, we know it's the circuit that's on bottom.
S5.
Yeah, we could go to S5.
okay, yeah.
So, and it's-
Yeah, so what I can do